Okay, this is problem 7-3, and the two main concepts behind the problem are: one, electric fields go from positive charges to negative charges. So electric field will go out like that. And then two, the strength of an electric field is directly related to kq over r squared. So the further away it gets, the weaker it becomes. So in part one, the problem, there's a equilateral triangle with points A, B, C, and there's a point charge Q at each of the vertices. And so it asks you to find the electric field at P1 due to each of the charges. Well, since the electric field comes out of positive charges, and they're all equidistant from P1, all of the vertices are equidistant, the electric field lines would go out like this, in a straight line from each of the different vertices, and it would be the same magnitude for each one. And in the next part, they ask you for the same triangle, but now they're asking for the electric field at P2, which is slightly lower than P1. So at P2 it would still be in this direction, but the magnitude from A would be less because it's further away, and the magnitude from B and C would be greater because it's now closer to these 2 points. In part B of the problem, it's still the same triangle, but now they're asking why anywhere along this y-axis, why there's no electric field in the x direction. This is because points B and C are equidistant from the y-axis, so this is the same distance right here, D and D. So that means that anywhere along this line, if you have like a point here, electric field from B would be going here in this direction, electric field from C would be going here in this direction, and so their components would cancel out, or their horizontal components would cancel out. That means the net electric field at this point due to these two would only be in the vertical direction, and since this is on the point A is on the y-axis, so there would be no component of this electric field going in the horizontal direction. In part C of the problem, you have the same triangle, and they ask you to find the electric potential at any point on the y-axis. So if the point, let's just say it can be anywhere on it, but let's say it's right here. Okay. Basically, for electric potential, you have to understand that it's equal to the sum of kq over r. So you have to look at each of the individual charges and then see how far away they are from the point. So let's just say that this distance right here is RA, this distance right here is RB, and this distance right here is RC. So the electric potential would be K times QA over RA plus QB over RB plus QC over RC. Now, since B and C are equidistant from the horizontal, or from the y-axis, this means that the RB is actually equal to RC, so you can rewrite this as K times QA over RA plus QB plus QC over 2R, over RB. And since all the point charges have the same magnitude in this problem, you can just write it as just Q for all of them. So it's just Q over RA plus 2Q over RB. Now RA, the two values that they give in this problem are that this right here from B to C is L, and Y would be from this x-axis over here, which Y is this height over here. So you can use these two lengths to figure out what RA, RB, and RC are. So since this is an equilateral triangle, it's given at the beginning of the problem, you know that this length right here is L over 2, since that's only half of L, and then that would make this length, this entire length over here, from the A to the bottom, would be square root of 3L over 2, because it's a special right triangle. And so that means RA, this height right here would be equal, RA is equal to square root of 3L over 2 minus Y, because it's this entire one minus the short portion gives this. And then for RB, you can just look at this smaller right triangle over here. You know that RB is equal, if you use Pythagorean theorem, you can figure out that it's equal to L squared over 4, this length squared, plus Y squared. This length squared gives this. And so once you know these values, you just plug them into here, and that gives you your answer. For the last part of the problem, all you need to know is an equation on your equation sheet, which is E is equal to negative dV over dr. Electric field is equal to the negative derivative of electric potential. So for this problem, you just need to realize that if you set electric field equal to 0, and then you plug in whatever you had from part C for electric potential, and then take the derivative of that with respect to Y, and then solve for Y, that'll give you the location of the point where the electric field is equal to 0. And that's it.